Hey everyone, and thank you so much, Azul Prime Time, for having me today. My name is Simon, I'm a developer advocate at JetBrains, and today I'd like to tell you about scalable agents with Koog and Ktor in Kotlin. So, when we build any kind of application, we are always going to be needing some kind of configuration. And in this case, we need a host and a port for our server, and we need an API key for our agent. And this is how we define it. Typically, in any backend service on the JVM, we define an application.yaml file or an application.hocon file or something like that in the resources folder, which is picked up by the framework, can then be loaded. And here we are preferring to load environment variables, and if those are not available, in the case of host and port, we are falling back on the fallback values. In the case of the API key, we always want to have an API key, and we do not want to provide a fallback value as a default, right? So in case there's no API key available for OpenAI, we're just going to crash the application. So how do we use this in Kotlin? Well, in Kotlin, we define a data class that has the same key properties or the key value pairs as our application file. In this case, the host, the port, and the API key. The order does not matter. And we can then use the application config type from Ktor to load the application file and turn that into a typed value of app config. And it's really convenient because it allows us to work with our configuration files in a typed way. So how do we start a server with Ktor? Well, we call the embedded server function and we specify which engine we want to use, in this case the Netty engine, which is the most popular engine on the JVM, but we also have support for Jetty, Tomcat, and a coroutines-based one, and potentially more. And when the server is started on Netty, we are also specifying the host, localhost, and the port 8080. And then inside of the Lambda block, we can describe our application. And what is important to note here is that the Lambda is a suspending Lambda, which means that this server or this Lambda is going to be running inside of a coroutine. And it is really powerful because it allows us to do concurrency and parallelism while we are starting our server. What's also important to note here is that we are here using start wait, but you don't have to do that. And Ktor is super lightweight, so you can use it to start many servers in the same JVM process. So combining these two things together, we first load the configuration in our main function. When we have the configuration, we are going to use that to initialize our server with the correct host and port. Right? Nothing too shocking here. What I do want to emphasize is that Ktor has support for more than just YAML and also comes with Hocon support out of the box. And here is, I think, a first important split that we want to make. So here within our DSL or within our embedded server, we have an entry point into our custom logic, right? So here we have described how our production server or potentially our development environment server is going to run, right? And we then delegate that to our code. In this case, a suspending function which has the application type such that we get access to Ktor and our loaded configuration. And we can then, for example, also use that same function inside of the Ktor test application, right? So that Ktor will spin up an in-memory server, and we can then interact with the server in a very fast way using unit testing. So here, there's no actual server started, and the client that we are using is communicating with the in-memory implementation of the test application. So we're almost finished talking about Ktor. There's still one more thing that we want to do, and is we want to stream the events that we are going to be generating in our agent. And to enable streaming or to enable server-sent events, we need to explicitly install the plugin. So I mentioned before that Ktor servers are very lightweight. That means that there is no or there is very, very little plugins, only the routing plugin is configured by default, right? And that guarantees that we have really fast startup time, but that also means that you need to explicitly enable features when you want to use them. Once we have enabled our SSE feature, or server sent event feature, we can use a server sent event DSL to, in this case, create a hello endpoint and send a single event world. What I again want to emphasize on is that this function is a suspending function. So we have the guarantee that it runs in a coroutine, and we have the guarantee that we can safely run any concurrent code, and we can even launch or create new coroutines inside. So we are going to be using that to, in a non-blocking way, start our model context protocol server. And that brings us to the agent part, or to the AI part. So I already mentioned model context protocol. Of course, this is supported by the Koog framework, just like custom tools, but it comes with so many more things. There's also support for persistent memory out of the box, very comprehensive tracing. There's support for building very flexible and very complex graph workflows. And all of this in a modular system, right? So also in a plugin system similar to Ktor, as we'll see in a little bit. And that allows for very scalable architecture where you can define and write code in such a way that you can reuse and compose it with different agents, right? And that is really, really powerful. So what is an agent? Well, at some point, something is going to start, right? And when an agent starts, as we all know, whenever we interact with an LLM, we ask a question, we give it a prompt, and that is going to start things, right? So we always start with a prompt, and then we call the LLM. Typically, when working with agents, we give the agent a bunch of tools so that it becomes smarter and it can interact with the outside world. So after our initial request to the LLM might finish, but it might also ask the framework or ask the user to execute a tool. When that tool is executed, it's going to send its results to the LLM, and then the LLM might finish or it might execute another tool, right? And it is this loop of the LLM calling tools in sequence until it is satisfied and it finds that it finished or solved the problem. Only then will it go to the finished state, right? So this autonomously calling the LLM and executing tools, it's what we call agentic behavior. And when we are building agents, we very commonly need to work with many different models. And most of these models are not always provided by the same LLM provider. So when building agents, we very, very commonly need to work with OpenAI, Anthropic, and Google, and maybe more. And in Koog, you can very easily do so by creating the clients and then putting them together in a prompt executor. And then this prompt executor will be used to execute the tasks or the nodes in the agent in the workflow, depending on which model you need, it will use the appropriate client. So let's build our first agent. We have our initial prompt, which is we need to travel from Copenhagen to Berlin. How can I travel and what clothes should I bring if I want to leave tomorrow? So we create our AI agent, we give it the executor, which has the different LLM providers or the different LLM clients. We specify the model that we want to use in our agent. And remember, in different steps within our agent, which we will see later, you can provide different LLM models, right? But in the case that nothing is provided, in this case, it will default back to GPT-4.0. But when we run this agent, we get a very generic, non-accurate response. Why? The LLM or the agent can only rely on the information it has, right? And we are not giving it access to any external information, right? So we're going to get a very generic, non-accurate response, potentially with hallucinated information. So we want to give it access to the outside world. And a very common way of doing that is using MCP, or Model Context Protocol. And in this case, we're using Docker MCP Gateway, which is a really convenient way to launch and host MCP servers on your local machine. And you can then specify the server, in this case, Google Maps. And we are then specifying 5 tools. And the Google Maps MCP server actually has a lot more tools, but I'm only specifying these 5 tools because I think, as the designer of the agent, that these are the only tools it needs, right? So if you give the agent way too many tools, if you give it too many tools, then it might get lost, right? Imagine yourself, if you give yourself an API or a framework with 10,000 APIs, it will be very hard to figure out which is the correct API or function to call in which case. And the same goes for LLM. So try to split up your workflow and try to give your agent only the tools that it needs when it needs them. So limit the amount of tools specific for the problems you want to solve. And we of course still need to go from our MCP server, right, which is a remotely hosted server, or in this case a separate container running on my machine, and we need to host that into the Koog representation, which is the tool registry, and we can transform that into the tool registry simply by calling the SSE, or the server sent event transport constructor here, or the static creation function, and point it to the URL, and that will automatically connect to the server, make sure everything works. And it also does that in a suspending way using coroutines. So now that we have our tool registry with Google Maps, we can now give it to our agent, and let's try running our code again. So if you run our agent again, we can now see that tools are getting called, right? And here it has called 7 tools, and you might notice that if you run the same program several times, that maybe at some point it only calls 5 tools, then maybe it calls 10 tools. This is the LLM that is trying to figure out what information it needs to give you the proper response, right? And this is not deterministic, so this might slightly change every time. What I do want to note here is that be careful with your tools and consider using caching, because in this case, in a single run, it called search place 3 times. It called map search twice. I could imagine that maybe it's searching something on the map and it is using the same parameters, right? So nothing is preventing the LLM from calling search places twice with the exact same arguments, right? And in those cases, you could potentially return a cached value depending on your use case, and that could save you tremendous amounts of money. Additionally, if you don't supply enough tools to your AI agent, it can very well be that your AI agent cannot solve the problem that you ask, right? So in this case, we asked it to travel from Copenhagen to Berlin, but it has no access to flight details. It also has no real-time weather information, right? So there's a couple of requirements in our original question that the LLM or the agent cannot fulfill. So let's write a custom tool for it. And we can simply define a Kotlin function and annotate it with tool. But that is often not enough. LLMs really like a lot of descriptions and very detailed information. So adding these LLM descriptions can actually improve the accuracy of which your AI agent calls your tools, right? So think very carefully about your descriptions and prefer to add more context than you would typically do for yourself, right? The LLM really benefits from this. And we do the same thing for the return type, and we are specifying descriptions all across the board. Remember, it's important that your types are serializable, such that Koog can use colonic serialization to transform your types into JSON and JSON schemas. So the implementation of our tool is pretty straightforward. To use the Ktor HTTP client to send a request to OpenMeteo. and we then receive the JSON body and we return the current weather value from the response. That's not too shocking. But what if something goes wrong? Right? Stack traces, especially in production environments, can be very, very long. Right? And if we would give that very long stack trace to the agent, then we are really bloating or potentially really bloating the context window. Right? Imagine that we had a chat history with maybe 10 lines of text, and all of a sudden we had a stack trace that is 200 lines of text. Right? We have now polluted our context with our stack trace, and our actual information gets buried in this large history. Right? So depending on the kind of failure and the possibility to recover or not, or if your agent needs to take specific action when something fails, for example, if you're working on a coding agent, when compilation fails, you want to give very detailed error information to how your LLM or how your agent can fix the code. But in this case, it's not really the case, right? We try to call a remote service. We can potentially retry 1, 2, 3 times. But if that still hasn't worked, there's really not a point in the LLM trying it again, right? So here we could potentially say an error occurred with the API request, and that's it, right? The LLM now knows that it failed. It could try again, or it could just decide to move forward. And we need to do the same thing for our actual result, right? So if you noticed here, I changed the return type from current weather to tool result. That allowed us to return the text message in case of the error. And in the case of our success value, we are now just going to return the JSON. And remember our LLM descriptions from before. Those will also be included in the JSON schema, so the LLM knows the descriptions of the JSON that we are sending here. So now that we have our tools from the MCP server and we have our custom tool, we can combine them with the plus operator, and that gives us all the tools from both tool registries, and we can then pass that to our AI agent. And now if we run our prompt again, we will get much more accurate information. So how do we interact with our agent? Because in this case, we are running the agent and we are waiting for the final results, right? So if the user sends a request, it needs to wait until the agent is completely finished until it gets a response. And that is a really bad UX. So what we want to do instead is we want to emit events, agent events, from the agent so that we can stream them to the user. We can do so by relying on the feature context, right? So remember, we had install plugins in Ktor. We also have install plugins in Koog. And this happens on the feature context. And on the feature context, we can call the install function, and we can use that to install the event handler. We can then, for example, register the onTool call handler, and if onTool call is called, we are emitting that event to the outside world by invoking the lambda. Similar, if we have a tool call result, we are sending that to the outside world through our handler. And finally, same for when our agent finishes, we're also sending that event to the user. So now we can actually build a UI that will show the user we are trying to figure out how you can go from Copenhagen to Berlin. We have fetched the weather results and we now know that it's going to be this kind of weather, and then finally get the summary which has the answered original prompt, right? So we can now give the user some feedback along the way of what is happening, and that gives the user a feeling that something is happening instead of just looking at a loading bar for maybe 15 or 20 seconds or maybe even longer. So how do we put this together, right? So we have our server sent event route handler, and in our route handler we can get a question from the query parameters, and we can then send or run our agent given the user question, And we are emitting events, or we are sending events through our event handler, right? So remember from before, whenever a tool was called, whenever a tool had a result, or whenever the agent finishes, we will get invoked here, and we are sending those events as JSON over the server-sent event stream back to the user. Right, so now the user will get a stream of events of what is happening inside of the agent. System prompts are also super important. And we have noticed that Markdown works really well for LLMs, right? So Markdown has a very simple but clear structure, and that can help the LLM understand better what is required to do. So for example, here I tell it you are an expert travel assistant. I'm explicitly listing the tools that it has available, and I'm also telling it that it needs to only call tools, and it needs to continue until it has answered all the questions from the prompt, right? And these kind of practices are quite common if you look around in agents in different systems. This brings us back to strategy. So I mentioned in the beginning, or I mentioned a bit back, that this is the default strategy of an agent. But there is many different strategies. And you can build these strategies in Koog. And we provide many different strategies out of the box as well. And one of those strategies, the one that we are using in our example, is the single run strategy. And it's the simplest strategy that you can find in Koog. And it creates 3 nodes. It creates a node for calling the LLM, it creates a node for executing the tool, and it creates a node for sending the tool results back to the LLM. And then we can start connecting the nodes. So we have our node start, which I said always exists, right? And so the same is true for our DSL. And then we go from node start to calling the LLM, right? So that is this arrow. Then we go from calling the LLM to executing the tool when we have found a toCall, right? So when we find a toCall, we go from call LLM to execute tool. And we go from call LLM to finish when we get an assistant message. And an assistant message is here a response from the LLM, right? So the LLM is giving us a response. It's not asking us to execute a tool, so we are considering it finished. And the finished node is also always available. However, when we encounter a tool request, we are going to execute it and send that result to the LLM. That leaves us with 2 options. After executing or after calling the LLM with the tool results, it might call another tool or it might finish, right? So this is where this loop gets created, where after it calls a tool, it comes back to the LLM. It has an opportunity to call another tool again. And that is how we can design graphs in Koog in a typed way. So all of this is type checked, and this guarantees you that you don't make any silly mistakes. I already mentioned that it's very important to think about your context window, your chat history. So it becomes also very important to compress the history if you have long-running agents that accumulate a lot of context along the way. And you can do that with this very simple function, in this case by creating an LLM compression history node, which you can then wire in your graph. And you can also apply custom strategies. So here we are saying chunk the history into 20 sizes and compress the history by keeping these kind of chunks. And you can customize this behavior by implementing your own history compression interface. So to summarize, I hope it was clear that thanks to Kotlin Coroutines, we can have seamless concurrency in streaming. Right, there was very little complexity in terms of concurrency in streaming. The only thing that we saw was the suspend keyword. I think it's also clear that Ktor and Koog offers us these typesafe DSLs for scalability and confidence. And these kind of architectures that rely on plugin allow to compose and reuse components in your architecture, which allows for a lot of scaling. All of these frameworks and libraries are efficient, lightweight, and built with performance in mind, because that is also not critical for our users, but this is also critical for the products which we build on top of Kotlin and Koog and Ktor and so on. Finally, I want to thank you all for listening to me today. I want to thank Azul for inviting me, and I want to mention that Kotlin is being used a lot in the AI world. There's the Scalable framework by Rod Johnson, which is written in Kotlin. He's the inventor of Spring. You can find his talk on the KotlinConf YouTube. The OpenAI and the Anthropic Java SDKs are actually written in Kotlin. So if you're using them from Java, you are also already using Kotlin, and you can find today's example on my GitHub repository. Thank you all so much. It was my pleasure being here. I hope to see you again.